All right, we are live and back from break. I hope everybody is totally energized for this last step. Got your coffee, got your pastries, whatever it is you need to wrap up the rest of this day. Our next speaker is going to be our last official talk of the day. We have a special event coming up after that. I'll mention a little more in a few moments, but I would like to invite Max to the stage. Max, welcome. It's good to see you.
It's great to see you. Thank you for having me.
Yeah, good. Max is no stranger to the, at least for me, front-end developer. Max is no stranger in terms of the many libraries, utilities, companies that you've been a part of up to this point. So really thrilled to have you here. Super excited for one of two talks you are giving today. So thanks for being a hero on that. I'm going to give you as much time as possible here to actually present your talk and your content for us. So I'm just going to hand it right over and take it away.
Thank you for that lovely intro, Jesse. That was very, very nice of you. I am super excited to be here and talk to you all about how to edge cache GraphQL APIs. Like Jesse said, my name is Max. I am one of the co-founders of GraphCDN. And if you have spent any time in the JavaScript ecosystem or in the React ecosystem, you might know me from some open source projects I've created, like Styled Components, React Boilerplate, Microanalytics, a whole bunch of them. I love open source. I'm a huge open source nerd, and so I've spent a lot of time in that community specifically. The story of how I started to think about GraphQL caching starts in 2018. I was the founder of another startup at the time, as the CTO of a startup called Spectrum. And at Spectrum, we were building an online platform for communities. Essentially, we were trying to take the best of what PHP BB gave you 15 or 20 years ago with the best of what Slack and Discord give you nowadays. We were trying to create a public real-time forum where, honestly, mostly open source people and open source users and developers could connect and chat with each other. But the whole idea was that all of these conversations were publicly indexed on Google. And so when you were searching for an issue you were having with an open source library, for example, you could find the conversations that people had already had on Spectrum. That was our idea. And that idea very quickly gained a lot of traction. We got a bunch of big open source projects on the platform very quickly, and our user growth exploded very early on. Suddenly, my job as the CTO changed from let's build something that maybe some people want and figure out if they want it to, okay, now you have to very suddenly run this infrastructure at scale. Our servers at the time were not literally, but they were on fire. We were crashing every single day. I Googled in preparation for this talk, I Googled servers on fire, and I found this amazing stock photo on Shutterstock of a data center rack with fire overlaid. I have no idea why anyone made this picture. Our data centers didn't literally look like this, but they felt like it. We were literally crashing every single day. We had downtime every single day. And you can imagine, as a community platform that people use day in, day out, that was a nightmare scenario, right? We had all kinds of scaling troubles, and most of them actually came from the database layer. I had at the time chosen a database that unfortunately wasn't very well supported. It's called RethinkDB. It's a NoSQL database. And the reason I chose it is because they advertised it as the real-time database. And their killer feature was that you could append a thing to every single database query and get a live feed of any changes to the data. So for example, if you had a query that fetches the list of posts in a community, you could put .changes at the end, and you would get a subscription, and you would essentially just get pinged anytime a post was edited or added or removed, which sounded like an amazing fit for what we were trying to do, right? Like, we were trying to make this real-time, public real-time platform, and we needed everything to be real-time. And so I thought, the real-time database, we should probably use that. That sounds like a great fit. What I didn't know, and only figured out as we were having all of these scaling troubles with it, was that this real-time nature was only added to RethinkDB at the very end of its lifespan. The company behind it hadn't found a lot of traction with just building a general database that was better than others. And so they were like, well, what can we do that doesn't exist yet? We're just going to make the database real time. And so they sort of plugged that feature on at the end, and it just wasn't built very well. Our database server started crashing as soon as we had more than 50 to 100 change listeners. Now, you can imagine every single user that was looking at Spectrum was opening up dozens of change listeners, right? One for the list of their communities, one for the posts in the community, one for the likes on those posts, one for new messages in posts, one for their user data. We were trying to make everything real time. And so every single user kicked off 3, 4, 5, up to a dozen change listeners. We have a very specific use case, right? We were a public forum. So all of our data is public, and all of it is basically the same for every user, right? Every single unauthenticated user that visited Spectrum saw the exact same data. Now, authenticated users also saw some of the same data, but they also saw some custom data, right? Like whether they liked the post before, which of the messages were their own, where they were the author, etc., etc. So the sign-in view was a little bit different, but the unauthenticated view was the same for everybody. We were also using GraphQL for our API, which worked out amazingly well. GraphQL allowed us to ship quality software much, much faster than we could have done otherwise. We were able to traverse our data graph very quickly. And as you can imagine, we were loading like the list of communities that the user was a member in, the first 10 posts in that community, the community metadata, how many likes and comments each post has. We were loading a lot of data on every screen, but that was really simple with GraphQL, and that actually worked really, really well. And so we had this very specific use case, and we were using GraphQL, and in my head I was like, well, why, we have this public, very read-heavy use case. That's basically a perfect scenario for caching, right? If we could just put like caching in front of our GraphQL API, basically all of our scaling problems would have went away, because it would have dropped our database pressure by a lot. Like we were looking at, 95% reads and maybe 5% writes, if not even more. And out of those 95% reads, probably 90% of those were from public unauthenticated users just reading the content and finding it from Google. So it would have probably reduced our database pressure and our infrastructure pressure by a factor of 10, maybe, if not even more. And so I was like, okay, hold on. We use a GraphQL client on the front end that allows us to fetch GraphQL queries, and then that GraphQL client caches them in the browser, right? So that when a user navigates between different posts, the data that they previously loaded, they don't have to load it again. Can't I just take that GraphQL client, that caching, and run it at the edge, right? Why can't I just take that and put it in front of my entire API rather than just having it for one user? I want to have it for every user, right? And share the cache between them. To answer why that isn't quite as simple as I maybe thought it was, let's take a look at how GraphQL clients cache. Imagine a very typical GraphQL query where you're fetching a blog post. In this case, we're fetching the blog post with the slug GraphQL itch caching, and we're fetching its ID, title, and the author. And of the author, we're fetching the ID, name, and avatar. Now, there's one magic trick that is built into every single GraphQL API that actually makes GraphQL ideal for caching. And that magic trick is the __ type name meta field. Every single object in a GraphQL API exposes this field. And so we can add it to queries even automatically, and we can go, okay, give me the type name of the post field and give me the type name of the author field. Now, the server will fetch, of course, all of the data, the ID, the title, the author, and then it's going to return that data to the client. And when that response comes back, it's going to look something like this. We have the post with its title, as well as the author with its name, with their name, really. Now, why the type name matters is because now we know that this response contains the post with the ID 5, as well as the user with the ID 1. And we know this because of the type name that the API responded with. We know that the top level data that we fetched was a post, and the author data that we fetched, it was a user. And GraphQL clients now take this response and put it into the cache. And they store it in the cache and they tag it and they say, look, I have this response, and this response contains the post with the ID 5 and the user with the ID 1. Now, why does that matter? Why do we need to tag what we put in the cache? How is that relevant for anything? Well, the other thing that GraphQL does is it differentiates between queries and mutations. In REST, this is usually done with get versus post. In GraphQL, the body of the post request tells you whether it's a query or mutation. So imagine we have a mutation that is an edit post mutation, right? And that gets an input, and in this case, we're editing the post with the ID 5, and we're slightly changing its title because we discovered that it's a better title. And as a response to that, of course, comes back the post, and we're going to fetch its ID and title again. We can do the same thing that we did for the query. We can add the _ type name meta field. So when this mutation goes to the API edits the post in the database and then responds with the new post data. When the response comes back, it's going to look something like this. Now, here is where the type name matters. The GraphQL clients, look at this and they know a mutation was sent to the API, and that mutation responded with the post, which it knows based on the type name, with the ID 5. So now the GraphQL clients can go, oh, hold on, mutation, change the post with the ID 5, let me invalidate any cached query results that contain the post with the ID 5. And that is magic. And that is why GraphQL clients can have this caching in the first place, because of the introspectability and the _ type name meta field that every single GraphQL API ships. So now the GraphQL client knows, look, I've cached this data, but I know what this data contains. And so when a mutation comes in, it can say, look, post with the ID 5 has changed. Well, I just invalidate the cached query result that contains that data and refetch that query from the origin to show the user the fresh data that they just changed. That's super powerful, and this magic works really, really, really well. Now, unfortunately, this magic doesn't work perfectly. There's one edge case, which is list invalidation. Imagine a query that fetches a list of posts, right? In this case, we're fetching all the posts we have, and we're going to fetch their ID and their title. Now, again, we're going to add the _ type name meta field, which I'm not going to show you anymore now. But the response to this query is going to look something like this: an array of objects, and the first object is the post with the ID 5 with its new title. Now, imagine a query where we create a post. So we're not editing an existing post, we're publishing a new one. And so we create a post, whatever we want its title and body to be, doesn't really matter. And then we fetch the ID and the title of this new post as the response. So this API passes through the GraphQL client, goes to the API creates the post in the database, stores it somewhere, associates the author with it, and then returns it back to the client. And the client sees a response that looks something like this. It's the post with the ID 6 that has some title. Doesn't really matter. Now, the big problem here is that the posts query, the list of posts that we had fetched earlier, doesn't contain the post with the ID 6. So the GraphQL client sees, okay, a mutation was just passed to the API, and that mutation responded with the post with the ID 6, but we don't have a cached query result that contains the post with the ID 6, right? We just do not have that in the cache yet, and the post list doesn't contain it, so the GraphQL client can't know that it has to invalidate the list of posts. That is the one edge case that this magic invalidation has, and as a solution, GraphQL clients ship something called manual invalidation. And so, for example, with Urkel, which is one of the biggest GraphQL clients, you can define this updates key, and you can say, look, if you, Urkel, the GraphQL client, see the create post mutation, please invalidate the query.posts query, because that list of posts that was returned has to have changed now that there's a new post, right? So just invalidate it from the cache and thus trigger a refetch from the API and fetch the fresh data. So this works quite well, and essentially you just have to add this little bit of code to annotate which lists you have. And GraphQL clients can do a lot more advanced stuff with the cache as well. You can automatically add the new data to the list and stuff, but this is the most basic version of how to do the manual invalidation. Now, this is sort of the basic of GraphQL caching. And what this is usually called is document level caching, because we're taking the entire query result and storing it in the cache. But there's an even more advanced form of caching, and that is called normalized caching. And in fact, this is what most GraphQL clients nowadays do. Usually they have a setting to enable or disable normalized caching or an extension of some form, but all of them support this. And this is usually the default behavior because it is more powerful. If we go back to our query where we were fetching a single blog post, right? This one. We're fetching the blog post and we're fetching the author. If we look at the response again, we have the post with ID 5 and the user with the ID 1. Rather than taking this entire response and storing it in the cache as a response for this specific query, normalized caching takes every object in the response and caches it separately. So for example, with Urkel, their data structure looks a little bit like this. It stores the post with the ID 5 in the cache. It stores the post with the ID 5 with the data of that post, and then the user with the ID 1 with the data of that user. Why does that matter? Well, if you now have another query that comes in and is like, well, look, I want to fetch the data for the user with the ID 1, then the cache can say, hold on, you haven't sent this specific query before that fetches the user with the ID 1. However, I have the data for the user with the ID 1 in my cache already because you fetched that data already with the post because that was the post's author. So we don't actually have to go to the API to fetch this data anymore. I can just respond with it from the cache immediately, which makes for a much nicer user experience and takes a bunch of load off of your backend, because that means you're essentially only ever fetching every object once and then never again. Really powerful per user, of course. Again, this is all happening in a user's browser. Now, what you might notice here, what is missing is, of course, the post author, right? We know that the post with the ID 5 has an author, that is the user with the ID 1, but that information is lost here. And that's because Urkel stores these relations in these links, I think is what they call them, really, in a separate data structure that looks a little bit like this. And essentially what that's saying is, hey, if the query for the post with the slug GraphQL edge caching comes in, that corresponds to the post with the ID 5. If we're fetching the author of the post with the ID 5, that corresponds to the user with the ID 1. Those are the relations we have. And then, of course, you have the user with the ID 1, but that doesn't have any further links, any further relations. So that is how GraphQL clients do document-level caching, and they also do normalized caching. Really, the takeaway I want you to have from this section is that GraphQL is awesome for caching because of the type name meta field, because of the differentiation between queries and mutation, because of the introspectability. GraphQL as a standard is actually fantastic for caching. It's I would almost say it's ideal, minus the one edge case of list invalidations when you're creating new objects. GraphQL is really, really, really good for caching, hence why there is so many GraphQL clients now and why all of them have this built in. It's really powerful and it makes for a really nice user experience when you do it in the browser. So with that out of the way, let me go back to my original question. Can't I just run a GraphQL client? Can't I just take the same goddamn logic and run it at the edge? Now, the big problem here, of course, is the edge. The big difference between running this in a single user's browser and running it at the edge for many users is authorization, right? Because suddenly you're no longer dealing with only a single person's data. If you run a GraphQL client in the browser, and that cache has data in it, the cache doesn't need to know whether you have access, it knows that you have access because it is the same user every time. So it's just going to send you the data. No matter if it has it in the cache, it's just going to give it to you. At the edge, that isn't true, right? Just because I'm fetching the same query from my local edge in Vienna, for example, doesn't mean that I'm the same user, right? Somebody else in Vienna might have requested that data just 10 seconds ago. I am not that same user. And so in many cases, I should not be seeing the same data, particularly if it's private data, right? If we're talking about user data, authenticated user data, you can't just have a simple cache. Now, the solution to this, of course, is to extend the cache key from just the query to also include the authorization token. So in our case, it usually looks like a hash of the query plus a hash of the authorization token. And that way you ensure that every response that is specific to a user, if a certain user requests some data, you're ensuring no other user that is authenticated will get that same response to ensure that no private data can ever leak. The other thing that's different is invalidation, because suddenly you're no longer talking about invalidating data locally in memory in a browser. You're talking about purging data globally, right? You're talking about many data centers. You're talking about cache responses that might be in all of them or none of them or some of them. So how do you do this? Well, thankfully, we didn't have to solve this. We use Fastly's Compute@Edge product. And Fastly's Compute@Edge product essentially lets you run custom code on Fastly's infrastructure. Fastly has about 60 plus worldwide edge locations. They're constantly adding more, and they're obviously maintaining that infrastructure. But they let you run code on there. And so you can write similar caching logic to what GraphQL clients do with a few minor adaptations. And then Fastly has incredibly fast invalidation. So Fastly's purging takes about 150 milliseconds globally. To put that into perspective, blinking once with your eyes takes about 300 milliseconds. So literally, faster than you can blink with your eyes, Fastly will have invalidated any cached query results globally that contain any specific object. And that's how GraphCDN can very quickly invalidate data, right? If you tell us, hey, if we see a mutation that the post with the ID 5 has changed, we can invalidate any cached query result that contains the post with the ID 5 within 150 milliseconds globally from all 60 data centers. And that was really the major key, because once you have this fast invalidation, you can basically cache any data, right? Of course, if it's super real time, it's not going to work. But if you have a read heavy use case with data that changes not every second, but maybe every minute, every 10 minutes, every hour, every day, then you can achieve really high cache hit rates, because you can set time to lives to really high amounts. Because when the data changes, you invalidate it anyway, and it's gone in an instant. So that was the journey I went through. I wish GraphCDN had existed when I was building Spectrum back in 2018, when we were running into all of our scaling troubles. And so that's why we spent so much time building up this entire infrastructure and this GraphQL CDN, because this solved the problem that we had with our scaling troubles. And we wanted everyone else to be able to use our solution rather than having to go build this themselves, because it is a little bit more tricky than you might expect. All right, I hope you learned something today. Thank you so much for having me, API Days. I was really excited to be here. If you have any questions, put them in the chat, I believe, and I would be happy to answer them.
Yeah, fantastic. And I mean, what's what they say about cache invalidation, right?
Only two hard problems in computer science.
Yeah. Yeah, really great. Really, I mean, it's a great space to be focusing on, and it is something where as we see GraphQL just increase in adoption, it is going to need to be one of those things that everybody embraces, because will be the holdup. I'm just going to check here if we have a question there. Nope, just gratitude.
I'll take it. I'll take it.
So if you have any questions, post them in the chat, and Max will maybe hang out for a few minutes to be able to answer those in the chat there. Got to move on to the next talk here, but again, thank you so much for coming. Hope
thank you for having me
for your next talk. and yeah, thank you so much.